Yeah. And you are talking on universal transformations of data-driven models to control systems. Sebastian.
All right. Yes. Thank you, Michael. And welcome everyone to my presentation. I would like to talk about how to universally transform predictive models to control systems today. And before I start, let me ask the questions: why is such a model even necessary, or why is such an approach necessary? And the motivation is the optimization of complex systems. So if you think about aerodynamics in engineering, for example, or pedestrian flow simulations, or you have medical applications like breathing simulations and so on, these are usually very, very costly to do numerically, if models are even available. So in the case of PDEs on the left or fluid dynamics on the right, you usually have a very high dimensional discretization using finite elements or finite difference or something like this. And in the middle, in these agent-based simulations, you have a large number of particles, so that the number of unknowns is very large. So simulating these systems is quite expensive if you have models, as I said. And if you want to do parameter studies or control, this is even more costly. So the usual approach that people take is to collect data and then use this data to construct surrogate models that allow us to approximate the solution in much less time. So what you usually do is you collect snapshot data of your full high dimensional system, and then you use this data to in some way construct a surrogate model that allows you to predict the dynamics. And yeah, this has been done for quite some time, or for a long time, and many people are working on this. There's tons of approaches around, and you can use then these models for optimization and control. But there's a big challenge when you want to do this for control systems. And this is threefold. First, the modeling itself can become really difficult. If you have complex control inputs and so on, it is much more data hungry than the autonomous case, because if you have inputs, your system is usually no longer restricted to a low dimensional manifold, for example. And the modeling can be highly problem specific, not in just the equation you're looking at, but even the boundary conditions and so on. So this challenge is really repetitive. Once you change your boundary conditions, maybe you have to do the whole process again. So this is why a universal approach would be really helpful to approach this in a more systematic way. And this is what I would like to talk about today. But before I do so, I will give an introduction to surrogate modeling, and in particular into surrogate modeling in optimal control. And then I will talk about our approach to get this in a more universal framework. By the way, this is joint work with Katharina Bika from our group in Paderborn. And after I've introduced this universal transformation, I will talk a little bit about error analysis, how we can use our transformations to guarantee error bounds for the true optimization problem, and then I will discuss results in the end. Okay, so let's start with the general problem that we're looking at. This is our optimal control problem in a very general way. So we have a control function u that we want to determine in such a way that a cost functional j is minimized. And this j is the integral over some objective function p, which might be a tracking type objective. So we want our state y to track a reference trajectory, and y is the state of a differential equation. So we have a constraint that this y has to satisfy, in this case, an ODE. You could write this with a PDE as well, but I'm going to stick with ODEs here. And you could think of if you have a PDE as a, let's say, space discretization, and this would be a finite element version of a PDE, for example. So you have this problem that you want to solve. So you have to solve it repeatedly to determine the optimal input, that your tracking is optimal, for example. But as I said, we want to use data-driven models. And in this case, you usually have time series data that you use to approximate your dynamics. So what I will do is I will introduce a finite discrete version of the control problem. So if I fix my input u over or between two grid nodes of my time grid that I have now introduced, then we end up with this problem in the bottom, which I denote by 1 now, because I will be using a few other problems in our transformation approach. But we have this problem, which is equivalent to the one above. So the integral is replaced by the sum, and we have now, as a constraint, a discrete time dynamical system, which is linked to the one above by this time t map phi. And this phi is now the one that's expensive to evaluate. And due to the discrete time version, we have now not a control problem, but a high dimensional nonlinear optimization problem that we need to solve. And we want to replace the phi by something that's cheaper to evaluate. So, and how to do this? This is usually what's known as surrogate modeling. The reference 1 here is a very nice survey paper about projection-based approaches, but there are other ways as well. But the general approach of all of these methods is to replace the dynamical system phi by a reduced version phi r that does not necessarily predict the entire state y, but some observed quantity z. So there's a relation between your full state y and your observed state z by this observable function f. And this can now be of very different types. So your observable f could be the full state observable, so the identity, then you have z equals y. You could use partial observation or pointwise measurements. And you can also use arbitrary nonlinear functions of the state. For example, in this engineering example that I had in the beginning, you could calculate the forces acting on the surfaces. Or in this pedestrian example, this could be a quantity that depends on all individuals simultaneously or something like this. So we have this approach, replace the phi by some surrogate model phi r. And in the input case where you have an input, this has been done for quite some time as well, but still there exists quite a few challenges that make this really hard. For example, you have a larger surrogate model dimension. If you take a data, an entirely data-driven approach, let's say you build a neural network, then for control-specific applications, you usually have a larger network architecture, you have higher data requirements, and you have a more expensive training process. So this is something that makes this challenging. But also if you take the more classical route to do state augmentation, this is more complex to generate. So what you do in this approach is you take your input u and you just treat it as an additional state. So you have a larger state y hat. And for this, you can now just write down the autonomous system. But obviously the system dimension increases. And as I said briefly in the beginning also, this y hat is usually no longer constrained to a low dimensional manifold any longer. But if your system is controllable, this y hat can fill the entire state space. You have a large dimension, you need larger surrogate models and more data. And the second problem is that modeling is usually very problem and even model specific. So if you take proper orthogonal decomposition, for example, I'm not going into the details how this works, but many of you will know this. What you usually do is you collect data, snapshot data of your high dimensional system, and then you use this data to compute a low dimensional linear subspace on which you can project your system efficiently. And then you take this subspace and project your equations onto the subspace, and then you have a low dimensional model. But the problem is in POD that this is usually done for PDEs, where you have your state y depends on space x and time t, that you need to satisfy boundary conditions, obviously. And if you want to have any chance that your surrogate model mimics the dynamics of the full system, you need to ensure that your surrogate model satisfies these boundary conditions as well. And this cannot be done if these are non-homogeneous or even time dependent. So what you need to do is you need to go to a complex series of modifications of your data set so that you end up with this y tilde that has 0 boundary conditions everywhere. And then you can do POD. But you see, it depends on the boundary conditions. It's pretty tedious, and it's also very hard to stabilize. So this is problem specific. And what you also can do is you can exploit specific properties of models. For example, the Koopman operator it's well known that it's linear. A linear operator predicting the dynamics of the observable function f. So you need to exploit this linearity, but this is also an issue that you now need to tailor to your specific choice of model. And if you look at autonomous systems on the other side, this is much more general and I would say more advanced. So there's approaches like the Koopman operator. I've listed quite a few papers in the bottom, but there are tons of them. We have neural networks, in particular LSTMs or reservoir computers. There are stochastic modeling approaches like the Moritz-Zwanzig net framework or others. So, and the list goes on and on. So there's tons of researchers working in this field, and there's very, very good methods to predict dynamics. And what's even more important, for many of these approaches, we even have convergence results or even error bounds. So for POD, this has been known for 20 years now. You can bound the error between the full system state or the trajectory of the full system and the reduced model trajectory. For the Koopman operator, there are asymptotic results, but the last two papers here are also precise bounds for the prediction error. And there are other ways for linear systems with noise. You can use finite data sets to approximate these and so on. So you have really a very powerful and large framework to predict autonomous systems. So the question that I'm asking myself now is, can we use these results for control in a more universal way? And the follow-up question then would be, if the modeling of autonomous systems is so much more advanced, why don't we just use these models and adapt the control problem instead of vice versa? And this is what we are going to do now. So we want to modify the optimal control problem, and we do this by a quantization approach. So we have a control set, a bounded control set U, let's say the interval between a lower bound and an upper bound. And we now replace this by a finite set of inputs V. And this might be just the bounds themselves. So it's a set with two entries or with two elements. And this now allows us to rewrite the control problem that I had in the beginning. So it looks basically identical. The only difference is that we now have here this set V instead of the bounded or the set U. So you can see that this is not much has differed, only that I now have to choose my U from a finite set. But in the constraint, this allows me to replace my non-autonomous dynamics by a finite set of autonomous systems that correspond to these different entries in V. So I have M, I name the number of elements in V M. I have M autonomous systems, and I can now use these M autonomous systems instead of one input system. So this is the problem that I had on the slide before again. And the question that we need to ask ourselves first now is, does this work or doesn't it work? So because I have changed the possibilities to pick my inputs, is this working, yes or no? And the answer is yes. And it's been known since the 60s by Filipov and Waszewski. And it says that if the reachable set corresponding to U is contained in the convex hull of the reachable sets corresponding to the entries in V, then the set of trajectories corresponding to V is dense in the set of trajectories corresponding to U. Meaning that as long as we pick our V in a good way, or as we, let's say for control affine systems, we just pick the bounds, then we are fine. So we need to pick it in a good way, and then these trajectories are dense. But we now have to solve a combinatorial problem with infinitely many switches. So basically we have shifted the difficulty to the control side. Now I'm going to look at this problem one again, and I can do also the discrete time problem. I can do the same transformation here, where I just replace my U by this V. And I now have a combinatorial optimization problem with m to the power of p possible input choices, and it's the same as in the continuous setting. So I have an objective function that I want to minimize, and I have to pick, and each time it's between one of these m different right-hand sides. So this is more challenging because it's combinatorial, but this allows me to simply use any model order reduction technique that I want to replace my time t-map phi by phi r. I'm not even required to replace all of these individual maps by the identical model. I can just pick any predictive model I want. So this is the huge advantage. The surrogate modeling becomes easier, the control part becomes more challenging. And the question now is not how do we do the surrogate modeling, because we have established this. The question now is how do we solve this optimization problem efficiently, and more importantly, even how do we guarantee optimality? And there are several approaches to solve this problem 3. The first one, and the most obvious one, is to just directly solve it using, for example, total evaluation. If my number of inputs is not too large, I can use dynamic programming or other methods from integer optimization. So there are approaches, but these are usually very costly, and there are all combinatorial. There's no way around this. Or there is one way around it. I can do yet another transformation, and this has been developed by Saga, Bock, and Deal. It's known as convexification. So instead, what I do is the objective function is the same. The input is now not the u inside a set of finite input choices, but it's this variable omega. And the right-hand side, or the right-hand side of my dynamical system, is now not one of these phi maps, but the convex combination of all these maps multiplied by this omega. And I have the constraint that the sum of omega needs to be 1. And in combination with my definition of omega, that it has to be either 1 or 0, this is identical to the problem 3 that I had before. So I just precisely, I picked the omega in such a way that I picked precisely one right-hand side in each time step. So I've changed basically nothing, but I can now use relaxation. So I replace my omega, that has to be either 0 or 1, by alpha, which is in the interval 0 to 1. So this now is a continuous problem with m minus 1 times p variables. So I have m alpha entries for this convex combination between my m systems, but the last one can be neglected because I have this constraint that the sum needs to be 1. And I have a time horizon, a prediction horizon of length p. So it's m minus 1 times p variables. And before I had the dimension of u times p variables. So depending on my choice of m and the dimension of the control input, this may be slightly more expensive or not, depends on the problem. But this is still now again a continuous problem that I can solve basically with identical methods than the original problem 1. And I can apply the relaxed solution u star to the system. So I just compute my optimal input u star as the convex combination of these different autonomous control inputs. For control affine systems, this works. Or I can round this alpha star to omega star. So I just do a rounding procedure, and I will go into details in a bit how we do this. And then I apply this rounded version to my true system. Okay, so we have now a way to do this. And this now results in this scheme. And yeah, as you know, algorithms need fancy names nowadays, and we've come up with this one. It's based on these different steps. We have quantization. We started out with this problem 1. We pick u from this bounded set, and we have an input system phi, and we want to minimize j. We then perform the first step to quantize the control by replacing this set u by a finite set of inputs v. So we can do in this part, the simulation part, collect data for these different autonomous systems. Then we can do very easily this modeling step from 2 to 3, where we have an arbitrary off-the-shelf surrogate modeling technique like POD, Koopman operator, some neural network architectures, or whatever you can think of. And then we have this relaxation step back to problem 4, where we use this convexification relaxation approach to have, again, a continuous problem. So you see, we move from continuous control in the top to integer control, which is challenging for control. But we can then move from the full state to the observable space using surrogate modeling, which is easier in this lower part. And then we move back up to the continuous input and solve this problem 4. So this is now the loop that we are going to take. And the important question, obviously, is what do problems 1 and 4 have in common, or how good is my solution that I compute with problem 4 for my true problem 1? And this is what I will be discussing for the remainder of my talk, basically. First of all, I will discuss how this rounding procedure works to give a relation between the integer and the continuous control domains, so the upper part and the lower part of my sketch before. And this is done, as I said, by Saga, Bock, and Diehl using the sum-up rounding approach. So assume that your alpha entry is 0.5, then your classical rounding would suggest that it's 1 at all times. But the sum-up rounding can be seen as a rounding with memory approach. I'm not going to give the strict formula, but it's pretty straightforward. What you see is that the sum-up rounding takes past rounding decisions into account, and it rounds to 1 and 0 alternatingly, so that you have in the intermediate value a similar control as your dashed line. And if you have 0.8, then you see the rounding rounds to 1 in 80% of the time steps, and so on. So if you have a time varying input, the rounding would look like this. So this is a way to relate continuous inputs and discrete inputs with this rounding procedure. And what you can show then is that the integral over the difference between alpha, so the continuous variable, and the rounded variable omega, can be bounded by the number of entries in alpha and omega and the time discretization on which you perform rounding. So in the limit that you have infinitely many switches, these do not differ in form of the integral. And we can now use this to relate the continuous time system and the convexified system. So this is the first, what you can show. You have here our true system, the control input system, and we have here our system that is the convex combination of these different autonomous systems that are contained in V. So I have this bounded set U, I have a subset V, and G and Y need to be continuous, and U a measurable function. Then we can show that for any control function U, we can find a parameter alpha or a trajectory alpha such that we can bound the difference between these two right-hand sides, so to speak. So you see that we have a bound which depends on the final time, and this D, which is now the distance between the reachable set of our autonomous system and the convex hull of the reachable sets of these autonomous systems that are described by V. So this is what I had earlier with the Filipov-Wazewski theorem. So if we choose the D sufficiently many entries, or we pick it in a good way, then this error can become very small or even zero. In particular, for control affine systems, when we pick just the control bounds, then it's always zero. So we have related the original system with the convexified system. Next, we need to relate the convexified system with the rounded one, with the integer solution. And this is the original result by Saga, Bock, and Diehl, that's saying if the derivative, the time derivative of your right-hand side G is bounded as well as G itself by these constants C1 and C2, and you have the sum-up rounding procedures that guarantees that these two functions alpha and omega do not differ too much over your time horizon, then you can show that the difference in these two trajectories can be bounded by these constants C1 and C2 and this time step delta t. So you see, again, if we take this delta t sufficiently small, then we can guarantee that your switched system, your integer system, creates the same trajectories as your continuous input system. And we now can just combine these errors and apply the Grönwall lemma, and we can then see that for every control function u, we can find a function u bar, which is in this finite control set V, and bound the difference between the two trajectories. So you see, these are the two errors that I had before, the one depending on how I choose V. This second one is the discretization in the mixed integer reformulation. And then we have, via the Grönwall lemma, the dependency on the initial condition. So this is now a good way to relate these problems 1 and 2, so the continuous time and the continuous input and the mixed integer input. And from this, we can really easily have a corollary which says that the objective functions can become arbitrarily close. So if we now introduce this control to state operator S, which just maps y to u to y, so for each u, you generate a corresponding trajectory y, and your objective function p is Lipschitz constant, then for a solution y star u star of problem 1 of the continuous input problem, we can show that there exists a tuple y star 2 and u star 2 where u is in this set V, that the objective function values are close. So this is again the error as before. This one is due to the sum up rounding, and this is now a discrete version of this exponential term above here. And you see in the limit that we take delta t to 0, this latter term goes to p. So we see that as long as we discretize our system in a good way, we have arbitrarily close objective function values between 1 and 2. So I've linked problems 1 and 2 if I just pick the right numerical setup. And the question that we need to ask ourselves now is, what about the model error between 2 and 3? So the same arguments that I had for 1 and 2, I can use for 3 for the relation between 3 and 4. And if we want to close this loop now that I had for my algorithm in the sketch, I need to have a bound between 2 and 3. And this is now where I'm going to introduce an assumption and saying that we can bound this error and this bound is known. This may sound like a strong assumption, but as I said in the beginning, for many autonomous systems, there exists such a bound, so that I'm going to assume that we know this bound. Let's say we have a POD-based model, or we have this stochastic linear system where we can bound the error. Let's just say that the difference between the observation of the full system and the prediction of the surrogate system can be bounded by this error E that may, in addition, depend on the difference in the initial condition and the time discretization delta t maybe, but it could also be a constant. So I'm going to assume we have this error bound, and this now yields a time-dependent error E model as a function of Ti. So in the initial condition, we have just the difference between, well, the initial conditions of the two systems, and then this is just a recursive version of how the model amplifies over time. And when you now use, for example, to make this more intuitive, take the observable to be the identity, so it's a full state observable, and you fix your error to some constant value, then using again the Grönwall lemma, you get this exponential deviation between trajectories, which is very common in dynamical systems as well. So you see, this is something that we assume we can bound, and we can now use this to derive a bound between the objective function of problem 3 and problem 2, so the surrogate version and the full system version. And now a step that I need to take before I can do this, I need to see how the error between the full objective J and the surrogate objective JR, how these differ when I insert the same control. So for the same solution, how much do these two objective functions differ? And another assumption that I have to make is that the objective function evaluated for the full state is identical to the reduced objective function for the observed quantity. And this is, well, it's not that much of an assumption, because when you think about control, usually you need your objective function to be based on quantities that you can somehow measure or observe. So to put this observable in the objective function evaluation is not that, I would say, not that restrictive. But if we do so, then we can do some pretty straightforward calculations and see that in the end we end up with an error of this type. So we can bound the error between this full and the surrogate objective functions, and we can use this in combination with the model error to bound the distance between the objective function for the optimal trajectory of the surrogate-based problem and the optimal trajectory of the full model-based optimization problem. So we now have a bound for J of U3 and J of U2, and where the individual steps maybe are not so important. One comment I should make is that we can leave out the absolute value here, because if we think about the minimization problem with respect to the full system, then U star is the true minimizer. So this second term always has to be less than the first one, because U3 has been minimized with respect to my surrogate model, So we can leave out the absolute value, and then we can decompose this into 3 parts and use the estimate that we had on the slide before for the first and third term, so that we end up with this bound for the objective function difference between the surrogate model and the full model. And now we can just add these up using the triangle inequality. So we have the distance between problem 3 and 1, which is, as I show here, it's these errors that we had before. This is the distance between optimization problem 1 and optimization problem 2. This is the distance between 2 and 3, and we can just add them. And as I said before, for an appropriately chosen V, we have this M1 is 0, and the corresponding error, which I named EV here, is 0. If we take the time discretization delta t to 0, then this error M2 is 0. So that the only thing remains is this surrogate model-based part. So if I do my modeling correctly, this is the error I'm sticking with. And I've named it E1 here, because we can do something more if we do a few additional assumptions. Okay, but this is, as I said in the beginning, it's a combinatorial problem that can be challenging for control. So I'm using yet another transformation to this relaxed version. And I'm not doing all the math here in detail, just what I need to mention is I get another additional model-based error, and I get another of this mixed integer-based error, because I have to switch between continuous inputs and mixed integer inputs again. But I can do this. And if I consider linear observable functions, so f of y equals y, for example, or not only this, but f is linear, then I can, for this case between 1 and 4, get an error that's identical to the one that I had before. And an even better part is when I have control affine systems, meaning that my phi is phi1 of y plus phi2 of y times u, then I can have a very, very good bound for the difference between problems 1 and problem 4. So these are 2 continuous input optimization problems, and the bound is this EV, which I can get to be 0 if I choose V appropriately, so that all that remains is this model error ER that I had before. Okay, so this has been somewhat technical, let's say, but maybe here's an overview of what we can do now. This is the sketch that I had before. I'm starting in 1, then I'm going to 2 with the quantization, then I'm going to 3 with the modeling, and then I can solve problem 3, or I use the Summer-Browning procedure and solve problem 4. These are the error bounds that I can get. For example, the first one would be I solve a combinatorial problem for nonlinear observable functions and not necessarily control affine problems. I get this error bound E1. If I want to solve the same problem in a continuous manner, I need to use Summer-Browning again, and I get this error bound E2A. For linear observables, the bound gets sharper. And for control affine systems, I can even leave out this Summer-Browning procedure. So I just solve problem 4 and apply the convex combination to the real system, and I have this very, very nice error bound. So I have different approaches depending on the type of system that exclusively depend on the model error that I assume I know. And now let's go to the more, let's say, fun part and have a look at a few applications. I will start with this Dulfing equation, and I will construct this system in a way that I know the error, which means it's just a bias term I add in the second component. So I can bound the error precisely, and it's control affine in this case. So I adjust this u in the second component with relatively standard parameters here, and the control input can be between -4 and +4. And I now set this epsilon in such a way that epsilon times delta t is 10 to the -4. So the error bound between the two trajectories is also this 10 to the -4 term. And I can now derive this model error E model using what I've shown you before. So it's this recursive formula that just amplifies this E delta t term with an exponential term depending on the Lipschitz constant of my dynamics. But I can do all this, and now I have a model error. And now I set the final time t to 1, over which I want to optimize my system, and the reference trajectory is 0, 0, meaning that I want to stabilize the origin. And this is now what I get. So I have in black, in the top left, I have the optimal control solution of the true system. The solid line is y1, the dashed line is the second state y2, and you see that these both go to 0 here in the end, so it's very nice stabilization. And in the bottom left, you see in black, it's not that easy to distinguish from the blue line, the optimal control input that has been computed with, I've used Python for the calculation, the SciPy minimize algorithm. So I'm here in the end, and the blue line is now the control input that I have obtained by solving problem number 4. And you see that these are basically identical, and you see also the trajectories are very similar. So the blue one is not, you cannot see it because it's below the black line here. The dashed blue one is this one here. So it deviates. We have a constant offset that's due to the bias that I've added to the second component. But what you can see, and this is, I think, the most interesting part, is this blue shade, or this light blue shaded area. This is the error bound that we have proven. So you see, and due to the exponential term, obviously it deviates quite strongly in the end. But in the beginning, it's a quite tight bound that you can use very well for prediction and to prove how good your solution will be. And on the right-hand side, you see these error bounds. Again, for the red one, it's quite larger because the summer bounding adds another exponential term. As I said, you can reduce the orange error bound to the blue one by just reducing the time stepping. You can see this here in the top, these two lines are the same bound for just another delta t. So by reducing delta t, you could reduce this. But the blue one is basically the best we can get, I would say. And well, in the end, it's not much worse, even though the problem is working. But on short horizons, you see that it works really well. So this is now very well suited for model predictive control, meaning that we do not apply the whole control trajectory to the system at once. But if we think about feedback control, we just compute the solution of the optimal control problem over a finite time horizon, where p is not that large maybe, and just apply the first entry to the real system, which is running in parallel. And so you can calculate a feedback loop by solving this problem over and over again in real time. But we can do this as we have a cheap surrogate model. And then we have error bounds for our MPC, or for the optimal control problem that we can use very nicely for MPC. Okay, so and now I come to the results section. This is now a pretty busy slide, but the intention is to show you that this works for quite a large number of systems and surrogate modeling techniques. So what we have tried for systems is the Lorenz system, which is a chaotic ODE, the Burger's equation, which is a nonlinear PDE. We have a stochastic differential equation, this COVID-19 model, which has been popular quite recently. We've tested it on the Navier-Stokes equations, again a PDE, and the Mackey-Glass delay differential equation, which is also chaotic. So you see a very large range of systems. The quantization is maybe not that important here, but we do it in all the setups we have here. We do the same approach that I've presented you before. We quantize the control into a finite set of inputs, and then we use these to do our machinery. And we have different observables, for example, full state observation in the Lorenz system, or as we use proper orthogonal decomposition, full state for Burgers as well. Partial observations here, we have nonlinear functions of the state here, and also a partial observation of this Mackey-Glass equation as we observe only the state at time t. And then we can combine this with different surrogate models, Koopman operator, proper orthogonal decomposition. We have taken off-the-shelf LSTM or reservoir computing neural networks. And the lower part is now, well, you cannot see very much. I will go into the details for 2 examples next. But you see that all these perform really well. So we just took off-the-shelf modeling techniques and plugged them into our procedure and can control these very different systems quite efficiently. Well, yeah, as I said, these are quite small figures just to demonstrate that you can do this for many systems and many modeling techniques. Let's have a look at the Mackey-Glass delay differential equation. It's given here in the top left with these fairly standard parameters that give rise to turbulent or chaotic dynamics. And we pick our inputs as these three different input levels, and then apply reservoir computing as a surrogate modeling technique. And for those of you who are not familiar with surrogate modeling, it's basically recurrent neural networks. So it's not feed forward, but you have these loops. And so it would be difficult to train usually, but you fix this recurrent neural network and just train these output layers. So you just modify the weights of these output layers to have a training process to adapt your system to data. And what we can do now in our approach now is we can just train three different output layers corresponding to this 1, to this 0 input, and to this minus 0.2. So this is now the autonomous system. The training is quite easy this way. And this allows us to perform feedback control of the Mackey-Glass equation. And you can see that stabilization of the 1 is working very nicely here. So the error decays to 10 to the minus 4 in the end or so. So you see that this works really nicely. And we just collect data for these three different autonomous systems, compute these three reservoir computer output layers, and then we can do feedback control. Okay, and final example is the Lorenz system, to emphasize the control affine property or the importance of this. So we have these three equations with the input at the second component, and the objective is to do tracking of the second component. So you see that this sinusoidal curve should be tracked, and we see in the bottom that we can achieve this either with this orange line, which is the solution of our problem number 4, so the continuous solution directly applied to the real system. And we can also achieve this with summer Browning, which is this blue trajectory, but the switching happens so fast that it's, well, you just see a blue square, but this is the summer Browning solution. And you see that these work equally well for the control affine case. But if I now have a non-linear control dependency, we see that the summer Browning, we see that applying the continuous input gives rise to a quite substantial error, because obviously the system is no longer control affine. But the summer Browning procedure yields the same error as before. So we can do this for non-affine systems as well. Okay, and this is it. We have published the code in this GitHub repository, so feel free to download it if you're interested. And otherwise, thanks a lot for your attention.